think it's time for us to start, isn't it?
Okay, so it's time for us to get going today. And I'm pleased to make an introduction for Dr. Morrison, who is here after Pennington, who has a research interest in neuroendocrinology and physiology, and he's especially interested in the neuronal regulation of feeding behavior, body weight, homeostasis, reproduction, growth, metabolism. You've touched on it. So, his recent work is focused on dietary protein and how it affects food intake and body weight. In recent work in his laboratory, has discovered novel pathways contributing to the detection of protein restriction, and they have identified the circulating hormone FGF21 as the first known endocrine signal of protein restriction. So I'm going to turn it over to you and let you give us the details.
That's great.
Thank you.
Hello, everyone. I'll do my best to try to keep you awake this afternoon. So I'm just going to talk about hormones, signals in the brain, and mostly focus on food intake. But I want to start off by sort of acknowledging that these things are acting on more than just food intake. There's energy expenditure, and there's metabolism, and all these other things that the brain does. So we sort of use food intake kind of as a model. So feel free to interrupt or talk or ask questions if you want, and if we go long, I'll just skip slides and get to the end quickly. Okay, so I'm going to start with a question. I've used this question several times before, and audience participation is encouraged but not required. But so the question is, why do you eat? So, anyone, why do you eat? For energy, for nutrients. Okay? Is that the only reason you eat?
Because you're hungry.
Huh?
You're hungry.
Because you're hungry, yeah? That's a good answer. Kind of same, right? You eat because you need food. You're hungry because you need nutrients. Is that the only reason you eat? Taste. Say that again? Social cues, yeah.
Bored.
You're bored. That's a good one. What else?
Components like macromolecules.
Yeah. Okay, so here are some of mine. Hungry, y'all said that. Time, have you thought about that? Often you eat because you have an hour at lunch. So you just eat because that's when you eat. Or because mom put food on the table, or whatever it is. Social settings, you kind of do that. We eat just because that's what we do. Boredom, you have boredom. Pleasure, I think we kind of talked about with taste, that a lot of times you've had a stressful day. You can have a drink, or you can have ice cream. And they're both kind of rewarding and soothing in their own way, right? So, the point I'm making is that of all of these, only one really touches on this idea of nutrition or nutrients. All the other are for other things. And I just want to acknowledge that as I move forward, we're going to talk about food intake and its regulation as a sort of nutrition or nutritional replenishment. But food intake and therefore obesity is much bigger and much more complicated than this sort of narrow view of it. So let's zoom in. Why do you get hungry? You kind of touched that. Hunger, of this list, hunger is the only one that really talks about food or nutrients. So why do you get hungry?
Energy deprived.
Because you're energy deprived, okay? Is that the only reason you get hungry?
Because you see somebody else eating.
You see somebody else eat, so some external cue triggers hunger, right? Okay, so y'all get 2 of the 3 I said. So one I said is time, and now I don't mean time like mom put food on the table time, but I mean you have biology that's driven by circadian rhythms, and if you eat every day at noon, and then by the time it gets to 1 or 1:30, your body is expecting food. So there's this sort of a circadian entrainment. It's not really nutrients, but entrainment. We also eat because of external cues. I think that's a great idea. You are not hungry, but then you smell a smell, or you see an image, or you have a memory, and that triggers food. And then finally, we are hungry because internal signals of nutrient demand. So that is what I'm really talking about here again, that our body and our brain are talking, and the brain perceives nutrient depletion, energy, but maybe more than just energy. And that triggers a behavioral response that we could describe as hunger or food intake. So I'm going to use 2 words, kind of science words, to describe that. One is interoception and one is exteroception. Have y'all heard of that words? So my lab, I would say, or my research, is focused on interoception and how that works. So interoceptive cues are cues which arise from inside the body and tell the brain about physiological status in general or nutritional status in particular. And that's contrasted with, we kind of talked about it, exteroceptive cues, which are in essence the five senses. So, if you're nutrient deprived, somehow that is signaled to your body in a largely unconscious way, and that drives or influences food intake or food choice. And that's different when you smell a smell, or you see a sight, or you do something else, and that triggers food intake or hunger, not really because you need calories, but certainly these two interact together. So interoception is this sort of idea of how does the brain know if you have eaten a meal, lost weight, missing a nutrient, and that through this pathway, changes in physiological state are somehow communicated to the brain. And that doesn't mean just starvation. It could be pregnancy, depletion of sodium or some other nutrient, loss of blood volume. I mean, you could think about any sort of thing that would trigger sort of a change in the brain and how it causes changes in food intake. Okay, so this is a figure I took from this review. I'm kind of using the review, but mostly because I like the figures. And I'm going to touch on three topics. One is meal size and satiety. The other is energy homeostasis. And the final is the sort of touching on what I am doing, and that is the detection of nutrient depletion. And you can sort of look at that. We have these little short-term satiety signals, more long-term body weight, adiposity, energy homeostasis signals. And those are all kind of converging on the brain. That's just sort of what we're going to talk about. So the first is satiety. You know, there's words satiety and there's words satiation and all these other things. But in essence, satiety is the mechanism through which your brain knows that your stomach's full, that you've just eaten a meal. And that leads to the cessation of a meal. So I think that satiation is the feeling of fullness that causes you to stop eating a meal, and satiety is the feeling that causes you to not eat for a period of time and then eventually start eating once within that sort of thing. But they're really very the same thing. And so there's two kind of mechanisms that drive this. One is neural and the other is endocrine. And I'm going to just briefly touch on that and how that relates to food intake, really. So you've all heard of the vagus nerve, I would assume. So we have the autonomic nervous system, sympathetic outflow, parasympathetic outflow, and the vagus is parasympathetic. And so it's this, all this parasympathetic information comes out, and the vagus is a specific nerve that comes out of your brainstem, and it in essence innervates all your organs. So your heart, your lungs, your gut, all that other stuff. And I think it's important to think of the vagus as two-way directional. So there's afferent information that goes up, and there's efferent information that goes down. So it's this constant talk between your guts and your brain, you know, your stomach and your brain. And so afferent signals related to gastric distension, stretch receptors go to your brainstem. Information around nutrients themselves or hormones produced in response to nutrients are signaled through the afferent vagus, goes up to the nucleus of the solitary tract, and then that goes to the DMV, motor nucleus of the vagus. So motor nucleus is something that drives outflow of motor output. In this case, not motor output like your arm, but motor output in terms of stomach function or stomach contractions. And that causes other effects. And there's one like a classic, Rick Rogers, who y'all may know, this sort of vagal reflex where when you swallow food, that is sensed, goes to your hindbrain, goes back down and causes your stomach to relax to accept that food. That's a classic kind of vagal reflex, you know, efferent and afferent. Okay, so the question is, what happens if you cut the vagus? Well, if you cut up here, your heart stops. That's a bad thing. So they often do a thing called subdiaphragmatic vagotomy. So they're cutting below the lungs so that that innervation is intact, but the innervation of the gut is maintained. Well, if you just cut the vagus, and you cut efferent information, all sorts of weird things happen in terms of gastric emptying not going right and other things. So what they've very sophisticatedly been able to do, I said that right, is just cut afferent information just from the gut. And the question is, if you did that, just to cut the ability of the brain to sense neural influence from the gut, what would happen to food intake? Y'all know? No? What happens?
You don't stop eating.
You don't stop eating? That's a good guess. Yeah. So what happens to food intake when vagal signaling is blocked? So this is, I use the word cut, but really they have it's subdiaphragmatic deafferentation is what really happens, SDA. So here's what an intact rat does, and they're using, instead of meals in terms of solid food, it's meals in terms of licks, because it's really easy to see licking and lick rate. So here we have 1, 2, 3, 4, 5, 6, 7 meals, and then they cut, and what happens? Two things happen. One is the meal size increases because the brain doesn't know your stomach's full. So all this food flows into your stomach and the brain doesn't know it, so meal size grows. But there's also a compensation, and that is meal number decreases. And so the result is that ergonomy doesn't really affect food intake or body weight. Well, I'll take it back. It doesn't affect total food intake over a long period of time. It doesn't affect body weight. But it does have big effects on food intake within a single meal. So the brain's ability to know that your stomach is full heavily depends on this vagal sensing. But the brain can then compensate for that by having fewer meals or more meals depending on what happens. So that's sort of satiety signal in kind of a nutshell how the hindbrain is controlled in food intake. So there's another thing called CCK. So it's produced in your intestines in response to food and nutrients. So it's a hormone released into your bloodstream. CCK does a lot of stuff besides influencing food intake. A lot of these gut hormones help food be digested and absorbed. It's kind of this interaction between the stomach and the intestines and the liver and the portal circulation and the pancreas. And all that's coordinated in part by endocrine action. There's a word called incretins, which help influence insulin secretion in response to nutrient digestion. But one of the things that CCK does is it acts in the brainstem. And in fact, they think that it primarily acts on the vagus to control food intake. But when you give CCK to regulate food intake, it kind of does the exact same thing as cutting the vagus, but in reverse. So CCK significantly decreases meal size, but that results in an increase in meal number, and again, no change in food intake. So initially CCK was discovered, there's a lot of enthusiasm. You can strongly suppress food intake, but if you just give it continuously or give it right before every meal, that meal is shorter. The animal thinks it's full sooner, but it just has more meals and compensates. So again, there's no real change in food intake. So I just want to briefly touch on the fact that there's more than just CCK. All these hormones are being produced: secretin, GIP, motilin, ghrelin, which we're going to talk about a little bit, gastrin, amylin, GLP-1, GLP-2. All this stuff is being produced by your stomach in response to food. Some of it's acting locally, kind of in an incretin fashion, and influence nutrients, to influence gastric emptying and all this stuff, which I don't really know that much about. And others are going to the brain to control food intake and other things. So it's really kind of this complicated mosaic of hormones that are all being released in control food intake and nutrient digestion. And the traditional feeling is that satiety signals primarily act in the hindbrain. And there's a set of studies that I want to show you because I think it's really kind of amazing, in which they've isolated or shown the real role of the hindbrain in the control of food intake. And this is using decerebrate rats. Have you all ever heard of a decerebrate rat? It's kind of gruesome because a knife cut is made through the brain and it isolates the forebrain. So all neural activity is cut. So the only thing left is the hindbrain, the cerebellum back here, and a little bit of other stuff. But the hypothalamus is gone, the cortex is gone. So none of that information, like I think about food, meaning that can get out because it's been isolated. So they only have the hindbrain. So what does that do when you only have a hindbrain? And I think, for one, it's amazing that they live in a way. That's kind of just amazing in its own right. But decerebrate rats actually do okay. So they will eat when presented with food orally. So you put food into their mouth, they will chew and swallow it. So all that motor pattern of chewing, swallowing, digesting, all that's intact. They'll stop eating when they're full. Now that means you put food in their mouth and when they stop eating, they just sort of stop swallowing, it dribbles out. They can distinguish sweet from bitter. They can respond to some hormones like leptin, ghrelin, and CCK. But I think this is important what the cerebrate cannot do. So one is it can't voluntarily seek or approach food. So you have to feed those rats orally. you put food in their cage, they'll just sit there, there's no motivation, because there's no cortex. They won't approach food and consume it. But if you put food into their tongue, like you cannulate them so that you can sort of pump feed them or you orally feed them, they'll eat, swallow, and stop eating when they're full. They also won't respond to caloric restriction or reductions in meal frequency, and that's going to lead us to this idea of energy homeostasis and what the hypothalamus does compared to what the hindbrain does. So here's an example of what I mean. So if you take an intact rat and do two different things, it changes food intake. So the one is to look at, so this is a meal, a single meal, like Ensure in a bottle, like drink 15 mils, in a single meal. So if you give them a preload, so you gavage them 10 meals 30 minutes before, and then let them eat, of course they eat less. Their stomach's full, and you eat less. Or you deprive them for 24 hours, there's this adaptive hyperphagia. They know that they've been starved, and they compensate, they eat more. What about a decerebrate rat? Well, the hindbrain's intact, so that satiety within a meal kind of thing is all there. They will eat less in response to a preload. But what they won't do is eat more in response to food restriction. That sort of memory of nutrient status, that is not the hindbrain. So another example of that is, this is percent change in average meal size from 3 to 2 meals. So if y'all are eating 3 meals a day, and suddenly you only ate 2 meals a day, you would adapt by increasing your meal size. You eat more in those 2 meals. And intact animals do that, so they increase the size of their meals by 40% and they maintain their body weight. Well, if you take a decerebrate, that doesn't happen. They eat what they eat in a single meal, no matter if they're eating 2 meals a day or 7 meals a day. And therefore, when you go to 2 meals a day, they will lose weight. So you have to sort of continuously feed a decerebrate multiple meals to ensure that they get enough food. So again, the hindbrain is very important for the regulation or the sensing of fullness, satiety, satiation, motor patterns, and all that stuff. But it can't control energy balance or energy homeostasis. So we kind of talked about that. So the hindbrain is important for food intake within a meal, but not for long-term regulation of food intake. You need other parts of your brain to do that. And what do I mean by that? So here's energy homeostasis. This is some old work in rats from Ruth Harris, who actually was a faculty member here at Pennington a number of years ago. And I think this really nicely shows what I'm talking about, but y'all are all kind of familiar with this. So these are rats, and she starts tube feeding them, where she either gives them a specific amount of food, lets them eat ad lib, or she restricts their food. So the only food they get is being tube fed into their stomach, and it's a 40% food restriction. And so, of course, they lose weight. But then what happens when you stop tube feeding? Well, food intake or body weight rapidly goes back up. And that's associated with a spontaneous hyperphagia. Like that fasted 24-hour fasting, you have this post-restriction hyperphagia. So that causes body weight to go up. And I think it's also interesting that the opposite happens in response to overfeeding. So you overfeed, weight goes up, stop overfeeding, weight goes down, and that's associated with kind of a persistent decrease in spontaneous food intake. So your brain knows that if you gained weight or you've lost weight, and it changes food intake to compensate. And that is sort of this concept of energy homeostasis, that it's not short-term satiety, but these signals produced by energy stores or something like that are going to the brain and informing the brain of sort of where you are in terms of energy balance and fat mass or something like that. And the prototype of that is this hormone leptin that many of you have probably heard about. But leptin was discovered in these 2 spontaneous mouse lines. This is the OB or obese mouse and the DB or DB mouse, diabetic mouse. And it turns out that they are deficient in leptin or the leptin receptor, and they're massively obese. They're overeat, they do all sorts of things. So I'm going to use leptin kind of as the sort of example of how hormones, so adipositive hormones or energy balance hormones act in the brain. But of course there's more than just leptin. Lots of things are going on. We'll briefly kind of touch on that. So what does leptin do? Well, leptin is actually produced not by the gut, like CCK or GLP-1 or other kind of satiety hormones. It's produced by fat cells. And it's produced by fat cells in response to sort of fat cell size and nutrient status. Anything that drives glucose or carbon into a fat cell is going to make leptin go up. And anything that causes the fat cell to shrink or release energy is going to cause leptin to go down. And so leptin correlates really nicely with body adiposity in most settings. And most research would argue that a fall of leptin is really important for telling the brain that fat stores are low. And so OB mice, which don't have leptin, even though they're super obese, they always think they're starving to death. And so as a result, they're hyperphagic, they're hypometabolic or cold sensitive, they're infertile, their bones are short, inflammatory things are weird, they're broken in many, many ways. A very strange mouse. Because despite being obese, their body thinks they are starving. And so I think this is a really good example of how leptin regulates food intake. This is, again, a lot of this is kind of old data, but here they took a group of normal mice and they gave them leptin with a mini pump in kind of a chronic infusion. And so when they start, I think what's kind of fascinating, food intake immediately goes down and stays down for several days, and while it's down, they lose weight. But then they plateau and achieve a stable lower weight. And during that period of time, food intake is really not very different. I would bet that if you sort of had a large enough N, that you would see it slightly lower than wild type. But it's kind of like, you know, that other data is like the tube feeding in rats, because as soon as the leptin is stopped, they suddenly sort of wake up and say, I've been starved for 3 weeks. And they compensate by overeating for several days, rapidly regaining that weight. Maybe not quite, but rapidly regaining that weight. So just like underfeeding and overfeeding cause these compensatory changes in food intake that help normalize, just giving leptin, and this is ICP, just giving leptin into the brain sort of resets the body weight set point in a way, and they go back to a certain level, and you take the leptin away, and they kind of wake up and say, and adaptively respond back to that. So that's kind of energy balance in a nutshell with just one hormone, which is what CCK doesn't do. CCK does not do anything like this, and bigotemy doesn't do anything like this, but leptin does, and you can see why there was a lot of enthusiasm for leptin early on, that it can just sort of correct body weight and produce stable changes in weight loss. I also think it's important to know that you can't make an animal starve to death by giving it leptin. It will eventually go to a lower set point and then stop. There may not be any fat. I did one study where we gave lots of leptin into the brain of a rat, and when you sacrifice those animals 3 or 6 weeks later, you can almost not find any fat. So they burned up all their fat, but their skeletal muscles, all there intact. So it really is kind of a fat hormone that's driving adiposity, not as much body weight, but adiposity, sort of thing like that. I think it's also important to know that leptin does more than just food intake. It also influences energy expenditure, energy metabolism. So, you know, a lot of work in the clinic with Ravis's lab is focused on this kind of adaptive response to starvation. And this is work from Rudy Leibel's lab several years ago in humans. So if you take a human or a rodent or anyone and you cause weight loss, I think this is 10% weight loss, they're not only changes in food intake, but they're adaptive changes in energy metabolism. So total energy expenditure falls, non-resting energy expenditure falls, and I'm not completely understanding what this is, but this is somehow the efficiency of work. You know, the ability of skeletal muscle to do a set amount of work. The muscle becomes more efficient. So your body is doing everything it can in response to starvation to conserve the energy stores it has. You don't know when food's going to be available again, so everything becomes more efficient. And if you give leptin back to those people, you block most of that. So when you're starving and are losing weight, you're hungry, partly because leptin is falling, but all this sort of adaptive changes in energy expenditure, muscle efficiency, all that is also due to a fall of leptin. There's work that suggests that fall of leptin triggers infertility, reproductive compromises. You know, those little gymnasts are super fit, but they have no body fat and they don't cycle sometimes, or long-distance marathon runners. So the loss of body fat has a negative impact on reproductive function. And not all of that is leptin, but a lot of that is a fall of leptin. So it's this hormone that's signaling starvation to the brain, influencing food intake, from my kind of research, but it's doing all sorts of other things as well. So I think this is some work we did that no one ever notices, but I think is really kind of interesting because people often say the leptin is a hormone that just is responding to fasting, but I think it's also important to know that it's protecting its weight gain as well. So we replicated that data that I showed you with Ruth Harris. We cannulated stomachs of rats and pumped food into their stomach. They gain weight, as you would expect, and they stop eating, as you might expect too. At least they stop voluntarily eating. We're pumping food and liquid food into their stomach. But what I think is important is that when you stop pumping, they are persistently under-eating for several days after that, and body weight's kind of going back to normal. So it's just like that tube feeding over study that I showed you with Ruth Harris. So we wanted to see, is leptin important for this at all? Is leptin contributing? So we took a group of rats that are Zucker fatty rats. They don't have leptin receptors. The leptin receptors don't work. To ask if leptin was necessary. So Zucker fatty rats are called fatty for a reason. Their body weight gain is much more rapid and they're hyperphagic at baseline. So this is the control Zuckers. So you see they eat way more than the normal, so lean and obese. The obese are the Zucker fatties that don't have leptin. And what we were interested in is if we pump food into them, what would happen to food intake during the pump, and then what would happen when we turned it off? And so this is that data. So they started from a higher baseline, and we were able to suppress food intake with the infusion. So all that kind of brainstem, satiety stuff is intact. But what I think is amazing is that as soon as we turned the pump off, it went right back to normal one day later. So as normal animals sort of persistently suppress food intake and sort of lose their way off, if you take leptin away, it's as if they don't know that they were overfed 24 hours before. It's kind of, I thought that was kind of interesting. So leptin is not just, a fall of leptin is not just important to signal starvation or fasting. It's also, I think, that a rise in leptin is helping to suppress gains in body weight. Because these animals gain weight, and you take, in a leptin intact, they lose that weight off. If you take the leptin away, they don't lose the weight off, at least not as well. I think there's certainly other things besides leptin. But that ability to suppress their food intake for a long time is completely lost. Okay, so briefly, where does leptin act? So leptin acts all over the brain, actually, but most of the work is focused on this area of the brain, right in the middle, at the bottom of the brain, called the hypothalamus, and in particular this area called the arcuate nucleus. So these are leptin receptor GFP marks. They have green fluorescent protein in neurons that have leptin receptors. So you can see that leptin receptors are all over the place. You can see it even better on this screen. So all these different parts of the hypothalamus, dorsal medial hypothalamus, lateral hypothalamic area, ventromedial hypothalamus. I'm going to talk a little bit about the brain, but not too much, because you also have Hans Rudy who's going to talk to you, and Heike Munzberg is going to talk to you. And I'm expecting them to talk a lot more about the brain and neurons and neural circuits. So I'm going to try to leave that to them and just kind of talk in generalities. So of all these areas of the brain, the area that's mostly focused on is this little spot at the bottom of the brain called the arcuate nucleus. And you can see there's a ton of leptin receptor expressing neurons in that one little brain area. And in there are multiple populations of neurons that express leptin receptors, but two are most kind of notable. One is, and they're named for the neuropeptides they contain. So one are MPY-AGRP neurons, this neuropeptide MPY, and the other agouti-related protein. And the other is pro-opiomelanocortin, or POMC. And this is a little simplistic, so this is definitely simplistic, but I think it kind of shows kind of how things work. So we have one population of neurons that are orexigenic and the other that are anorexigenic, and you can kind of think about them as like a car, simple analogy, of the accelerator and the brake. So orexigenic neurons drive food intake, they're the accelerator, and anorexic neurons suppress food intake, and they're the brake, and leptin is working on them in opposing fashion. So if you had a car and you could only accelerate, you could have some control over speed, but not a lot. If you had a car that you could only brake, you'd have some control over speed, but not a lot. But if you can do both, you can kind of fine-tune that. And leptin is doing both. It's both stepping on the brake to suppress food intake, and it's also letting off the accelerator. And a lot of work has been focused on these two populations of neurons and how important they are for food intake, especially these AGRP neurons. They're like the darlings of neurobiology of food intake these days, and I'm hoping that Hans Rudy shows you some data, but I'm going to briefly show you why there's so much enthusiasm. So AGRP neurons, there's just a few hundred neurons in this. The only place they're expressed throughout the whole brain is the arcuate nucleus. Just these few little neurons down here. And if you make a mouse in which you can inject something that kills those neurons, the animals will starve to death. So if you just kill this one population of neurons in this one area of the brain, they'll die. They quit eating and they starve to death, and you have to rescue them. Interestingly, if you do that into young animals, they don't die. There's some sort of ability to adapt. This only works in adult animals. And if you do this and support them nutritionally for a week or so, you can get them through this crisis, and then they will live again. So there's both, clearly they're required, but there's also compensation and adaptation that goes on. But in an adult animal, if you just spontaneously kill AGRP neurons, which means you're knocking out AGRP, you're knocking out NPY, and you're knocking out anything else those neurons are producing, the animals quit eating and will die. And they had to, this was a science paper several years ago, and they had to say we had to stop doing this for animal welfare concerns. If you use dread stimulation, or dread technology to stimulate AGRP neurons, so I'm not going to talk about the cell biology of optogenetics and dread, because I know Heike will talk about it, but dread basically means you put this little switch into just this population of neurons and allow you to flip the switch. So you can just stimulate these neurons or just inhibit these neurons. So that's what optogenetics and dread are, two different ways. But in essence, you're putting a synthetic on-off switch in a specific population of neurons in a specific brain area. So if you put the on switch into AGRP neurons and turn them on, just this population of neurons, food intake goes immediately up. And if you chronically stimulate these neurons, it goes way up, you turn them, you stop injecting, and it goes, by the way, it goes right back down. Again, kind of like they're being overfed. And this, they don't show it here, but this moment here, there's that spontaneous hypophagia that's occurring, right? Just like I showed in my rat stuff. So they think they're starving, even though they're gaining weight, because you stimulate these neurons, and then you stop stimulating them, and they realize, oh no, I'm not starving, I'm overweight, and they undereat and lose their weight off. So again, just this one population of neurons robustly controls food intake and body weight. It's both necessary, because when you kill the neurons, food intake stops, and sufficient to completely control food intake and body weight. So you can see why there's all this enthusiasm for AGRP and where they project, and what brain areas are sensing, and how do they regulate food intake. And there's been a lot of work over the last 3 to 5 years on sort of the cell biology and neurocircuitry of AGRP neurons. I'm briefly going to talk about POMC neurons. POMC neurons are the brain. They suppress food intake. And the same thing happens. If you use, I think this is optogenetics in this case, specifically put the on switch in these neurons, food intake goes down, body weight goes down. And if you knock out POMC, animals are obese. If you knock out POMC, humans are redhead because melanocortins are important for pigmentation, and they're obese. So POMC is very important for the regulation of body weight. And in fact, AGRP and POMC are similar. They both act on a common receptor called the melanocortin-4 receptor, and the melanocortin-4 receptor is the most common single gene cause of human obesity. It's very rare still, way less than 1%. But of all the various mutations that lead to obesity, MC4, melanocortin-4 receptor, which a GUTA-related protein is a melanocortin antagonist, and alpha-MSH, which comes from POMC, is a melanocortin agonist. So, it's definitely relevant to body weight regulation, not only in mice, but also in humans. Okay, so two populations of neurons robustly control food intake, and leptin directly regulates their activity, firing rate, mRNA expression, all that sort of stuff is leptin does. And then those neurons then project out to other places in the brain. Often people describe these as first-order neurons, which then project to second-order neurons in other spots, and somehow food intake changes. So the kind of question is, how does food intake change? What about AGRP neurons or POMC neurons, or leptin action in here in the arcuate nucleus, translates into changes in food intake? So I'm going to leave that just briefly to talk about ghrelin, because I think, A, I should talk about more than just leptin, and B, ghrelin's kind of important. So ghrelin is sometimes called the hunger hormone. It's produced by your stomach, but it's produced by your stomach when it's empty. So if you look at fasting, there's high levels of ghrelin, and you eat food, and ghrelin goes back down. And ghrelin also acts in the brain to increase food intake. So this is the very original study where they gave ghrelin to mice, food intake went up, and body weight went up. These are 2 doses of ghrelin. And what's unique is that ghrelin is the only hormone produced by your gut that's known to increase food intake. All the other hormones are satiety signals, or suppressive signals. CCK suppresses food intake, GLP-1 suppresses food intake, amylin suppresses food intake, insulin suppresses food intake, blah, 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 blah. Ghrelin increases food intake. And the idea is that there may be a little bit of a yin and a yang between leptin and ghrelin. Leptin is high when you're fed and ghrelin is low, and when you starve, ghrelin goes up and leptin goes down. Ghrelin inflects food intake in humans, so this is food intake in response to a ghrelin injection in humans. It also influences hunger, kind of a perception of hunger in humans. If you knock out the ghrelin receptor, animals gain, they're less obese on a high-fat diet, so this is males and females. Knockouts, they have lower weight gain and less food intake on a high-fat diet. And ghrelin is tapping into this same neural circuitry. So here they give ghrelin, you can't quite see it, but this is CFOS. So CFOS is a marker of neurons that fire or turned on. So ghrelin activates CFOS, turns neurons on in the arcuate nucleus. And if you knock out AGRP and NPY together, ghrelin's ability to stimulate food intake is lost. So again, it's targeting the same brain area as leptin in the opposite way. It does the opposite things to these hormones, but it's still tapping into this really potent neural circuitry that regulates food intake. So leptin and ghrelin regulate food intake by engaging not only the hypothalamus, but also areas outside the hypothalamus. And I just want to briefly kind of touch on this, because it kind of brings what we were just talking about together. So one thing that leptin does, when it acts in the brain to AGRP neurons or pyramidal neurons, that signaling somehow interacts with hindbrain satiety signals. And there's two good examples of this interaction. So first is the ability of leptin to increase the sensitivity to gastric distension. So here we have a group of rats. This is a single meal. This is that same kind of thing I've shown you before where they get a preload. You put so many meals of food in their stomach and they eat less at that single meal. They then give a dose of ghrelin that's very low and has no effect on its own. But when you combine that dose of leptin, the dose of leptin that has no effect with this kind of small preload, that has a big effect on food intake. So what leptin does is it increases the sensitivity to an acute satiety signal. Leptin makes sure you have smaller meals. So a certain amount of food, if you're full and you have high leptin, you feel full faster. And if you're starving, that same amount of food is not as satiating. So when you're starving, you have low leptin and you eat larger meals over time. And when you're well fed, you eat smaller meals over time because the same amount of food in your stomach will make you feel more or less full in response to that. So here's another example. This is those same Zucker fatty rats that don't have leptin receptors. And a single dose of CCK, if you give a wild type rat CCK, it suppresses meal size or food intake in a single meal. If you give that same dose, this is a low dose of CCK to rats that don't have leptin receptors, it doesn't work. Then if you take an adenovirus that expresses a leptin receptor and inject it just into the arcuate nucleus, just in that area of the brain that has AGRP and pyramidal neurons, you restore the ability of CCK, which only acts in the vagus and the hindbrain, to decrease meal size. So leptin in the forebrain, in the hypothalamus, is causing neural information to go to the hindbrain that causes the hindbrain to feel full sooner. That makes sense, right? Quicker in response to a given input. And here's the figure that I pulled out from that. So leptin is acting these AGRP pyramidal neurons, engaging other circuitry, and that goes to the hindbrain and makes the hindbrain feel full more quickly in response to food in your stomach, CCK, gastric extension, vagus nerve, all that other thing. So I think another thing that's important is that it also is influencing appetitive behavior or motivation for food. So these are leptin deficient humans, and they're doing brain imaging in various areas of the brain that are associated with reward. And so you give a person who's deficient in leptin and show them food associated or food cues, their brain just lights up and responds very vigorously to those food cues or foods themselves. They think they're starving. And then you give them leptin back, and that doesn't occur. And so the quote from this paper is that in the leptin deficient state, images of well-liked foods engender a greater warning response even when the subject has been fed. So a leptin deficient human who's well fed responds to food cues like a starving person. And then, if you give leptin back, well-liked foods engender this response only when they're fasted, which makes sense. You know, when you're fasted and you see a food cue, you're like, that food is very motivational and very rewarding or very salient or whatever word is correct. But in the fed state, it's not so much. But if a person has no leptin, even if they're fed, their brain acts like they're fasting. This is another figure that is in mice, and Hans really likes this figure, so he may show it to you too. But it's kind of cute, I think, in a way. It's food finding time. So they have mice in a cage, and they put a bunch of bedding in the cage, like 6 inches of bedding, and they hide a little piece of food down in there, and they record how long it takes the mouse to find the food. And it takes a normal mouse, a wild-type mouse, about 400 seconds to find this piece of food. But it takes an OB-OB or a DB mouse, a mouse that doesn't have leptin, that thinks it's starving, it finds it in like 4 times faster, in maybe 100 seconds. So an OB-OB mouse is very driven to find food. And it's not clear if this is motivation, or just their sense of smell is stronger, or what it is. But they find the food, because they think they're dying. And if you give them leptin back, you can increase the food finding time. And they turn the open circles of the highest dose, and they look back like wild-type mice. And the point is, this is appetitive behavior. It's not consumatory behavior. It's not the size of a meal or the actual consumption of food. This is moving to get food in the environment, which is sort of what appetitive or motivation. And there's a lot of evidence. If you're starving, and I ask you to work for food or give me money for food, you're going to work harder or give me more money for that food. That's kind of motivation. And if you're well-fed, you're like, no, I don't want to work for food. So leptin is tapping into that same circuit. All of that is working together. So leptin is reducing food intake in multiple ways, both by enhancing satiety signal, so reducing meal size and making you feel fuller in response to the same amount of food intake, but it's also making food and food cues less rewarding and less motivating. Or by reverse, if you are starving and have low leptin, it's making you feel fuller less quickly and making food cues more salient or more rewarding. And so leptin's acting in this archinucleus area to influence the hindbrain. It's working in this archinucleus area to influence VTA neurons, which express dopamine and all this reward signaling. And there's also evidence that leptin acts also directly in the hindbrain and directly in these reward areas. And for instance, ghrelin is doing the same thing, and all these hormones are kind of doing the same thing. So this is kind of the last slide for this. This is an old review that Hans and I wrote, but I think it still kind of sums it up. When you eat food, it enters your oral cavity, goes all through your GI system. And all through here, things are being produced in, the vagus is being sensed, hormones are being made, nutrients are being absorbed, and all of that sends vagal information. There's also, besides the vagus, there's taste receptors and other sort of sensory information that's non-vagal that also gets to your brain. All that influences food intake through the hindbrain. Then those nutrients are absorbed. They go through your liver and the portal circulation, and then they go out to the rest of the body, and then other hormones, insulin, amylin, glucagon, leptin, adiponectin, all this sort of information then gets to your brain. The nutrients themselves even get to your brain. And then it's this interaction between satiety signaling, reward signaling, and the hypothalamus as kind of the energy balance area that all sort of coordinates why you eat what you eat, why you eat little, why you eat less, and that kind of thing. So I'm going to stop there. How long has it been? I've got maybe 30 minutes, 15 minutes, and answer questions about nutrient selection and metabolic need before I move to our own little research area, which is kind of missing nutrients and depletion of single nutrients. So do you have any questions that I can answer about leptin, ghrelin, brainstem, hypothalamus, and that kind of stuff? Go ahead.
What role does genetics play in this? Or is this just more so diet and
No, so I think genetics plays an important role. So just like people are genetically more prone to hypertension, are more prone to weak bones, are more prone to weak eyesight, they can also be more prone to weak HRP neurons or weak leptin receptor or any of that. So any of this, all of this, just because it's your brain doesn't mean it's not under genetic control and that there are genetic predispositions. There's a whole line of rodents that were selected. So they took a group of rats And over multiple generations, they selected some to be lean on a high-fat diet and others to be fat on a high-fat diet over many different durations. And they call one diet-induced obese rats and the other diet-resistant rats. And if you give those rats leptin before they gain weight, the resistant rats are more sensitive to leptin than the obesity-prone rats. So they are primed to not respond to leptin, this hormone that tells you that you're full and you need to not gain weight. So definitely genetics plays a role all throughout that. So. Yes?
I have two questions. So what percent of the population would you consider to be leptin deficient, and how commonly is leptin testing done when you go to your practitioner?
So there was a ton of, leptin I think was discovered, cloned. OBOB mice were discovered in like the 50s. They just kind of spontaneously arose in the Jackson lab. And then leptin was cloned, the mutation was cloned in like 94, I think. And for the first few years, there was all this enthusiasm. This is going to cure obesity. There are going to be people out there who don't make leptin or have low leptin. And the result is none of that proved to be true. So there are leptin deficient people, but they are super rare. Like, I don't know, maybe there's less than 100 in the world. So most people make leptin just fine, and in fact tend to be this word leptin resistant. They are kind of like diabetics or insulin resistant, so they have high levels of insulin and the insulin doesn't work very well. Obesity is associated with high levels of leptin, but the leptin seems to not work so well. And there's a lot of work on maybe what are the molecular causes of leptin resistance, and can we enhance leptin signaling and that work. And in fact, some of the new obesity drugs are these combination therapies. One of the therapies is sort of kind of an acute weight loss therapy, and because acute weight loss increases leptin sensitivity. And the other might be leptin. None of this is reached the clinic, but in animal models. So you can combine leptin with something else, and it's much more efficacious. If you just give leptin alone to an obese rat, it doesn't work very well. But if you give analin or some other drug that kind of work acutely suppress food intake, that increases leptin's efficacy and there's a longer term effect. Okay, so what was your second question?
I think you, so you said it's not really done in a clinical testing for cancer.
The guy who discovered leptin made millions of dollars, sold it to Jeff Friedman, sold it to the company was in California. None of that really panned out. But I think that there's a lot of, for instance, Rudy Leibel is the guy who did the change in energy efficiency and how leptin blocks that change in energy efficiency with starvation. He and some others have argued that maybe leptin doesn't work if you just take, an obese individual and give them leptin. It doesn't work. But maybe it would work if you put them through some intensive weight loss intervention. They lose 20% of their weight, and then you give them leptin, and the leptin will help prevent that resistance. They're going to want to regain their weight back. Maybe that weight loss will enhance leptin sensitivity, and you can give leptin like that, and it'll sort of help them keep their weight off. So I think there's still stuff out there, but in a simplistic way, leptin is not the obesity cure that they hoped to move forward.
There's a whole book on the discovery and controversy about leptin. It's called The Hungry Gene.
There was I was a student worker at Pennington from 93 to 97, and there was a ton of enthusiasm during that window for leptin, and none of that really worked out, unfortunately. But still, the thing that leptin did do is that we wouldn't know about HRP neurons or POMC neurons or any of that without the discovery of leptin. So it has definitely, over the last 15 to 20 years, driven a huge explosion in sort of the neurobiology of food and body image. Anything else? Okay. So I've been talking a lot about food intake studies that look like this. A mouse in a cage. He can eat food. But he doesn't have much choice. He can really only do two things. He can eat more, or he can eat less. But that's it. And so this type of research, which I have done and others have done, is very good for measuring grams of food intake or kcals of change in food intake. But I don't think it really fits what we face, or even maybe a wild mouse faces in its normal life. We have a much more complicated landscape where macronutrients vary, energy density varies, palatability varies, accessibility varies, procurement cost varies, all this stuff varies. And we somehow navigate this to make choices. And so what I'm interested in is, do we eat for more than just calories or grams? So eat more, is it more than just eating more or eating less? And does our physiological needs shape our dietary choices? And I think there's a great example of how physiological need can shape dietary choices in the sodium appetite field. So, you know, just like there's energy balance or weight balance, there's water balance. Maintain a certain amount of hydration intracellularly and extracellularly, right? And that depends in large part on the amount of fluid, water you intake, and also the amount of sodium you intake. And it's been known for many decades that sodium depletion causes a preference for salt. So this is one of the this guy named Kurt Richter is a famous name on kind of homeostasis. And so he has a group of rats, and they're either drinking 1% salt solutions or 3% salt solutions. And here, this first little bit is the run-in. And you can see that they drink more water than they do 1% salt, and they don't like 3% salt at all. They don't really drink any of that. And then he does an intervention, which is an adrenalectomy. And suddenly, they like 3% salt, and suddenly they like 1% salt more than water. So what about an adrenalectomy causes that to happen? Why would an adrenalectomy increase salt intake? So the adrenal glands make something. Physiology and endocrinology. Yes, it makes epinephrine. Good guess. Not that.
Oh, is it,
It makes it makes some hormones. Not angiotensin, but close. Huh? Renin, close. So the renin-angiotensin system is very important for thirst. And a little bit sodium, but it's not the... So the adrenal glands make two steroid hormones. One is glucocorticoids, cortisol, corticosterone. It also makes a mineral corticoid, which is aldosterone. And aldosterone does lots of things, but the most important thing it does is cause your kidney to reabsorb salt. So an adrenalectomized rat has no aldosterone, it's peeing out all its salt, basically. And because it's peeing out all its salt, it's sodium deprived, and suddenly it likes salt. So a salt solution that it doesn't like at first, now it loves. That's kind of fascinating, right? Somehow the brain knows to like salt. So when sodium deprived, rats will drink salt solutions that were previously unpalatable, work very hard for salt solutions, will prefer salt over sugar or other previously highly valued flavors. And cues associated with salt, which were previously aversive, become very rewarding. So it's not just the taste of salt, it's anything that salt has been associated with in the past or in the future. And I have a video of this. Videos are always fun. I'm going to show a video. So to set this up, these are rats, and they have a cannula in their head that allows them to give liquid solutions intraorally. So it's a tube that allows it to come in, and there's a little cannula that goes down through under their skin and into their cheek. And so they can squirt solutions directly into their mouths. The rat doesn't have the choice of drinking or not drinking. It just gets into its mouth. And they get salt, which they don't like, or they get sugar, which they love. But in addition, they're in a little operant chamber where these little levers come out. And the lever on one side, the lever on the right side is going to predict sugar. And the lever on the left side is going to predict salt. Right? So the lever comes out, there's actually a noise for 5 seconds or so. Then the lever goes back in, and then they get their squirt of sugar or salt. And so what is funny is how they treat these levers. So the first will be, when this loads, the lever associated with sugar. There we go. So lever comes out, he's not getting any sugar, but boy, he loves that lever, because he's learned that that lever means he's about to get sugar. And maybe he's superstitious. The lever goes in, and now he's getting sugar. Oh, I'm really happy. So there's a lot of reward, a lot of motivation, and kind of superstition if you think about it. Here's the lever that predicts salt. He does not like that lever at all. Like he looks at it, oh, please don't give me salt, please don't give me salt. Lever goes in, and now he gets salt. So that's a normal animal. But what happens if you sodium deprive? Now he loves the salt lever. And what this is a paper by Kent Berridge. the animal has never actually gotten salt, and you'll see he doesn't actually get salt. So he's never gotten salt in a salt-deprived state. That's what is amazing. The lever that was formerly very aversive and not interested instantaneously becomes extremely motivational and rewarding. All because physiological state changed. And I think that's kind of neat, right? So here's their figure, and I think the sort of title says it all. Sodium depletion instantly turns a salt conditioning stimulus, or that basically means the lever, into a motivational magnet. And what he was arguing is that it doesn't require, exposure to salt when they're salt deprived. What was formerly aversive is immediately rewarding just because of a change. And that had no effect on sucrose. So they still like sucrose, but they love salt when they're salt deprived. And then you replete them, and they don't like salt, don't like the lever anymore. So again, kind of interesting. So what you like or want can depend on your internal state. And so what I'm interested in, are there other nutrients that are regulated in the same way? And what I'm going to tell you briefly is my story with FGF21 and dietary protein, because I think sodium and the drive for sodium and the drive for protein are kind of similar, not the same, but similar, and that FGF21 is part of that. So I use this example sometimes. We got hummingbirds, right? And hummingbirds eat nectar. Just probably because she's been on this other website. Hummingbirds drink nectar, and what's nectar? Well, it's sucrose, right? If you ever put hummingbird fluids or feed in your hummingbird feeder, at least my wife puts 25% sucrose in a hummingbird feeder, right? Very sweet, very energy dense. Hummingbirds have a tremendous energy need because they're flying all around and burning tons of calories for their body weight. So they have a massive drive to consume energy and have this super palatable, fairly energy dense solution. But did you know that hummingbirds are also predators? And that they spend a lot of their time hunting insects, and about 25% of a hummingbird's diet is in fact insects. So why would a hummingbird spend all this time and effort hunting bugs when it's got this very energy dense, very palatable nutrient source just sitting there in my wife's hummingbird feeder? And the answer is because carbohydrate, or sucrose, is insufficient to support life. They need other nutrients, most notably protein, but maybe minerals as well. And so somehow the hummingbird is balancing these two needs, this need for energy and this need for protein and other things. And the question is, how does it know to do that? And I don't mean know from I got to get my 6 insects today, or 7, or whatever it is, right? It doesn't know that way. But it knows physiologically, and somehow is making these choices. And do we make those same choices? And is it just protein or other things? So we know that essential amino acids are just that. They're essential. If you don't get essential amino acids, you won't grow. All these bad things will occur. So it makes sense that there might be a physiology that defends protein, just like it defends energy or salt and maybe some other things. And if there is that, what are the mechanisms? So this is a figure, large part generated by Roy Martin, by the way. If you take 2 diets that are isocaloric, but one is low in protein, rats overeat that diet. They somehow sense that they're not getting enough protein and increase their food intake in response to this dilution of protein in the diet. This is a group of rats that are run in on diets that vary in protein. And as the run-in diet goes down in protein, they're then given a choice of diets, one high and one low. And their preference for the high protein diet increases as the amount of protein in the run-in diet goes down. Right? So the more protein deprived, when they get the chance to choose, they choose for more, as if they kind of are spontaneously or homeostatically regulating. And that seems to occur in both mice, as you vary the amount of protein food intake changes, as well as humans, as you vary the amount of protein energy intake, total food intake changes. And there's a guy named Steve Simpson who's coined this term protein leverage, or protein leverage hypothesis, in which he argues that fluctuations in dietary protein can leverage large changes in total energy intake because protein is defended. And if you restrict the amount of protein, low protein diets cause overeating of calories in an effort to sort of avoid protein restriction. So we talked about energy homeostasis. So the question is there protein homeostasis? Is there some signal that communicates to the brain in response to changes in protein status or muscle stores or liver metabolism? What is that? And so that's what we've been working on. What is the protein signal? Where does it act? And what are the neural circuits mediating it? And I don't have number 2 or number 3, but I think I may have least some of the answer to number 1. So we did a lot of work early on looking at where could it be generated. You know, you eat food, it goes into your GI tract, it goes through your portal circulation to your liver, then there's muscle. And so all along this pathway, hormones could be generated. But what we discovered is that the only tissue that seems to really be responding acutely to protein restriction was the liver. So we started looking, are there any liver-produced hormones that might be linked to this? We thought that initially that it would be skeletal muscle, and we kind of just did a lot of reading on myostatin and all these other hormones that are muscle, IL-6, that are muscle-derived hormones. And none of that seemed very good. But liver, and what we learned, there's this hormone called fibroblast growth factor 21 that's produced from the liver in response to fasting, and it goes way up. So it was described as a fasting hormone. But if you think about fasting, yeah, they're getting less energy, but they're also getting less of everything else. And so we said, well, maybe, I wonder, is it possible that FGF21 also goes up when you're protein deprived? And the answer is yes. And in fact, the reason it goes up with fasting is not the restriction of energy, but it's the restriction of protein. So these are rats that are on a normal energy and they're placed on a low protein diet, FGF21 goes way up. If we then energy restrict them, FGF21 in fact goes down and the low protein diet is not quite as effective. And this is some similar work in humans. These are 2 trials that were done here at Pennington. One was PROOF, which is a protein restriction trial, FGF21 goes up. And this is the kind of famous calorie trial when they calorie restricted humans and it didn't go up. So energy restriction alone is insufficient to increase FGF21 in humans and may in fact cause FGF21 to go down. But there's several cases in which you take protein restriction and FGF21 goes up. And there's some situations, for instance, one is ketogenic diet drives FGF21, and they didn't realize it, but a ketogenic diet is actually low in protein, and we showed that it's the fact that the diet's low in protein that's driving, not because it's ketogenic. Okay, so FGF21 definitely is this hormone. It's known to go to the brain, but is it doing anything? And the answer is that if we take FGF21 knockout mice, put them on a low protein diet, they don't know that they're being protein deprived. So there's this increase that occurs in wild type mice, that doesn't occur in FGF21 knockouts. Low protein diets tend to stop growth in normal mice, and amazingly the FGF21 mice grow just fine. And that's kind of weird. If you ask the nutritionist, why does body weight gain stop in animals who are protein deprived? Most people would say it's because there's not enough substrate, there's not enough amino acids, not enough building blocks to drive that growth. But these mice are on that same diet that has very little protein, and they grow just fine. In fact, they grow a little bit more than their controls. So if that's true, which I'm still sort of not sure I completely believe this, but if that's true, it suggests that the reason growth is stunted on low protein diets is not because there's not enough protein. I'm sure if you're completely protein deprived, there's certain point there would be. But in this case, it's not because there's not enough building blocks, but it's because there's a metabolic or adaptive response. The animal chooses, in a way, not to grow, and that choice is due to the increase in FGF21. Another thing that low protein diets do is cause energy expenditure to go up. This is wild type mice over time. That doesn't occur in FGF21 knockouts. So, in our hands, if you put FGF21 knockout mice, they don't seem to know. They don't change food intake, they don't change energy expenditure, they don't change growth. Genes in the fat don't change. There's some evidence that genes in the liver don't change. All this stuff seems to require FGF21. The only thing that we've seen so far that doesn't seem to require FGF21 is effects on bone. I think the effects on bone may be intact, but there's actually some weird stuff there too, maybe. But we were talking about food intake, so I'm going to show you our recent food intake data. If FGF21 really is an endocrine signal of protein restriction, then its increase should cause animals to seek protein. Kind of like the sodium-deprived animal look for sodium. So you would think the protein-deprived animal would look for protein. And if FGF21 is this signal, it should reproduce that effect, right? It should cause them to choose protein. So this is the thing I've always been wanting to do, and we had to do all this other legwork in order to get there. But this last year, we've been able to kind of focus on this question. So here's the data. Several figures. So these are FGF21 knockout mice that are choosing between 2 diets, one that's a normal diet and one that's a protein-free diet. And when they get saline, so these are injections for 3 days, there's no effect on choice. If they get FGF21, it drives them to the high protein choice. Does that make sense? It goes up. Then you stop injecting and it goes back away. So when they get FGF21, they choose more protein. You could express this as a preference ratio. So a preference ratio is the preference for the high protein choice divided by total food intake. So that's this. You know, a 0.5 preference ratio means they eat the same. A 1 means they eat exclusively the high protein choice, and a 0 means they eat exclusively the low protein choice. So the FGF21 makes protein preference go up, and you stop injecting, and it falls back down. We did another one. These are wild-type mice that are getting FGF21 just into their brain. They're also on a different choice paradigm, and again, the injections cause protein preference to go up, and we stop injecting, and it comes back down again. But there was one problem with this. So it's causing, there's actually 2 other studies that I didn't show you with different combinations of diet and different injections. But in all cases, it drives into the choice of protein. But these are solid diets. So the diet has protein, but it also has carbohydrate. And the problem is, in order to raise or lower the protein and keep the diet isocaloric, we have to raise or lower the carbohydrate. So our low protein diets are high carb. So a skeptic could say, it's not the protein. They're not choosing protein. They're avoiding carbohydrate. And I can't argue with that. So we started thinking about, is there a way that we can isolate the protein and the carbohydrates from each other? And what we chose to do was to go to liquid and just put casein in a bottle, or just put maltodextrin in a bottle. So maltodextrin is a carbohydrate, but it's a starch. It's not sweet, but it's still pure carbohydrate. So we have pure protein in a bottle, and we have pure carbohydrate in a bottle. And would they choose for that in a way? So the first test was asked if we ran a group of mice in on a low protein diet, would they show it an effect in preference or consumption? So this is single choice, just one. They have water, and they have casein, and they have their food. And so when they have casein in the cage, they drink more casein, but they don't drink more maltodextrin when they have that. So it's a specific effect on protein intake, but not an effect on carbohydrate intake, which I think is kind of important. They're not just drinking more of whatever's in their cage, they're only drinking more casein. If we do a 2 choice, where both are in the cage, then they drink less malto and they drink more casein, and you can express that as a preference ratio, and with this really robust increase. So animals that have been protein deprived consume more casein in a single choice, don't consume more malto in a single choice, and go from preferring malto, see that a 50%, 50 means they like it, so a low number here means they actually drink more malto, to preferring casein. Kind of like the sodium deprived animal. You gotta think about that, right? They become deprived, and something that was formerly not preferred becomes preferred. So the question is FGF21 doing anything in this? And so this data is all like 4 weeks old. So I don't know this is true, I should say. I don't know this is true, but I think it might be true. So the first thing, if FGF21 is up in this situation, if we give FGF21, it should reproduce this, right? So we gave FGF21 into the brain of animals that were choosing between casein and malto, and it worked. It increased their casein preference. Now, it didn't go as high as a low-protein diet, but maybe we gave them, maybe it's dose, I don't know. But it definitely significantly increased preference, and this was just a single injection. So they got an injection, and then it kind of waned, and I wish this bar had stayed flat, but it didn't. So we're going to keep doing this. And then we did a study in which we put mice in which we had knocked the FGF21 receptor out just in the brain. So they're making FGF21, but their brain can't sense it. And we did them on the sort of 2-choice diet. So Cre negative means that they're normal, and Cre positive means they have no FGF21 receptors in their brain. And normal mice drink less malto and drink more casein, and the knockout mice don't. And the normal mice, the preference for casein goes up, and the knockouts don't. And there's only 4 per group, so we got to keep doing this to make sure it's real. But again, it suggests that FGF21 is necessary for their ability to know they're protein deprived and to choose casein. So, protein restriction triggers changes in food intake, energy expenditure, and metabolism. It also increases FGF21, and FGF21 is required for all of those sort of effects on the diet. And protein-deprived mice select for protein over carbohydrate, and FGF21 in the brain appears to be both necessary and sufficient to drive this effect. So if that's true, one other thing. There's actually 2 previous papers that showed that if you give FGF21, it suppresses sweet intake. And I was like, oh, what does that mean? But if you sort of think about that, pure sucrose is definitely low protein, right? And it fits really well that FGF21 would drive away from sweet and drive towards protein. Kind of think about the hummingbird. You know, he needs to make that choice, that swap. And so it's not so much, I think, that FGF21 is a protein signal or a sweet signal. It's a macronutrient imbalance signal, and it's helping the animal coordinate food choices, not in response to energy balance like leptin does, but in response to sort of macronutrient balance and maybe protein, but maybe not. We'll see kind of how that goes out. Is it more? Although I showed you that it didn't affect carbohydrates so much as it affected. They showed in this paper that it doesn't affect maltodextrin, it only affects sweet. So we'll see. So, kind of come back around. We have all these hormones that are all going to the brain, and I think that it's possible that FGF21, we can stick it down here, it's a liver-derived hormone that influences food intake and food choice, mostly in response to macronutrient imbalance and protein restriction. And I should acknowledge that Crystal did a lot of that work, as well as Diana and Madeline, and two former postdocs, Tara and Thomas, did a lot of the work with energy expenditure and food intake and all the other stuff that I showed you earlier. And that's all. Thank you. Any questions?
So when they're in the cage and they get either water or the casein solution, or they get the casein or the sweet, how did they,
Not sweet.
or the maltodextrin, or in that other study, I guess, sweet, how do they taste the casein?
Yeah.
Like, is there a specific protein receptor on the tongue, or is it something?
So that's a great question, and one we're sort of working towards. So I'll start with answering sodium, because I don't think protein, the answer is I don't know, but I don't think that protein and sodium are the same. So you have sodium receptors, salt receptors on your tongue, and they are hardwired to your brain, and when that rat becomes sodium deprived, as soon as it tastes sodium, it likes sodium, right? I think that there is umami, one of the flavors is umami, and it's sort of a sodium, monosodium glutamate. It's sort of a sodium with associated with savory and protein, but I don't know.
But aren't some amino acids bitter?
Yes, like leucine is very bitter, exactly. Casein is not actually so, they don't really want to drink casein. In fact, you have to put a little bit of saccharin in there to kind of make it. Saccharin is a sweet that's non-caloric. There's a little bit of saccharin in there, as well as it's equal in the maltose, just to kind of help them drink it. So I think that it's a learned association. So they experience the casein, they just kind of try it because there's also some evidence that protein-deprived or nutrient-deprived animals are more exploratory. They're more willing to drink strange flavors because they know they're missing something, and so they are more likely to go elsewhere. So mice drink stuff, they will try things, and so they sort of learn that they feel better, whatever that means, in response to casein, and they drink them. Now, I saw it. Within the first 24 hours, they had significantly increased. I thought it might take a few days for that casein preference to manifest, but Madeline has done it twice, and it's up on day one. So I don't know whether it's umami or some other flavor that's associated, or if it's this learned experience. One of the things we're thinking of doing is having, it's a long answer, putting flavors in there. So we could put cherry and grape into the bottle, right? So they associate maltodextrin with cherry, and they associate casein with grape, say. And we do that for a week, and then suddenly we swap. Would they follow the flavor, or would they follow the protein? If I'm right, I think they would follow the flavor for the first few days, because they're just using whatever cue is most salient in that solution to guide their choices and associate that flavor with whatever post-ingested consequences that they like. And so initially they're going to follow the flavor until they realize, oh, this isn't really making me feel good anymore, and then they'll shift it back. So we're thinking about doing that experiment, for instance. I don't know if that would even really address it. We could also get the umami receptor knockout mouse and see if they don't do some of this stuff. But I think there's a lot of evidence that food preferences are more than tone taste, if that makes sense.
I'm just thinking if we're making a choice between.
I mean, it is definitely taste.
Yeah.
But whether that taste is the driver or just a learned association of the mechanism in which they're making those choices. So. Okay?
Do we even
Go ahead. That's okay.
Do you know if there's a difference in any other gut hormones, like GLP-1, PYY?
So yeah, that's a good question, and I don't know the answer to that well. It is definitely true that if you gavage protein, or you gavage carbohydrate, or you gavage fat, or you gavage a mixed meal, that the induction of the gut peptides is not the same in all those situations. And there was even a paper published that suggested that PYY knockout mice don't suppress their food intake on a high protein diet. But if you start following any of that literature, none of it really goes anywhere, right? So that's why we thought maybe it's not a gut hormone, that's got to be something else. And to me, we just completely lucked up that it was that FGF21 was work. I know it's just blind luck that kind of happened. But I'm trying to make the most of it while I can. And I'm sure that there are probably, it's more than just FGF21. And it's definitely true that, I can't remember which one CCK is more regulated about that, or there's people who know those things, right, about how the gut hormones respond to different nutrients. But if you knocked it, I don't think if you knocked CCK out or knocked PYY out, that it would influence the choices that I haven't done that, but I don't think that it would. Yes, ma'am.
I think it was kind of the same. I want to know if, because you said that you're still making studies in this. So how do you just get into the FGF21?
How do we get there, right?
Yes.
It was lucky. Like I said, we were initially looking at muscle hormones. So to be honest, my original grant hypothesized that it was amino acids, and that leucine in particular was acting on mTOR and AGRP neurons to control this thing. And we did a lot of work to prove that it wasn't that. And I was very nervous into that because my hypothesis was wrong. We showed that leucine was important, but leucine could regulate food intake, but it wasn't the physiological regulator of low protein-induced hyperphagia, for instance. So we started saying, maybe it's something else, some other hormone. And the first guess was that it was a muscle hormone, like analogous to leptin. So a change in adiposity causes a change in a hormone like leptin, and the brain senses that. Maybe a change in lean mass causes a change in a hormone like myostatin or something else. So then we started thinking about the liver. And you kind of think about it, the liver is really well positioned because the blood that goes into the liver from the portal circulation reflects what you digested. And the amino acid composition of blood going into the liver is very different than can be different than the amino acid that comes out of the liver, because the liver is the primary organ for the breakdown of amino acids and the biosynthesis of whatever amino acids you can, serine, asparagine, all these other that you can actually make. All that's going on in the liver. And the liver buffers. So like if Tom Geddes puts mice on a methionine restricted diet, their blood levels of methionine aren't that low because the liver is buffering, it's changing. And when you put animals on a low protein diet, we did this, their levels, blood amino acids kind of go bloop, and then they come back to normal. And all the genes associated with amino acid breakdown fall, and the genes associated with amino acid biosynthesis go up. So the liver is sort of buffering your amino acids. So it's right there at the point to be the sensor. And so when we started thinking about that, we're like, maybe there's a liver hormone, and we started asking, looking, and like FGF21 goes up at fasting, and we said, let's test it. And we haven't stopped, basically. Okay.
Bear with me on that question, but I'm just curious because this idea of like restricting nutrients or micromolecules or whatever the case may be, and then there's a need or want for it by the body, why doesn't that work with things like vegetables? Because I know like there's an increase, like we're trying to increase consumption of vegetables, especially in kids, but why is it that, if they're not eating vegetables, in that case I guess it's restricted, that they don't desire, the body doesn't want them to eat?
So I can't answer that question at all, and I think it's good, I think that there are probably hardwired, some things are hardwired, like oxygen, and calories, maybe, and salt, and fluids, we talk about angiotensin, all that's very sort of tightly regulated. But then things become less tightly regulated, maybe, like I don't know that protein is hardwired, like when you it may be more of this learned kind of thing. And then what about potassium, minerals? And what about vitamin C? And when a person is vitamin C deficient, does their brain know it? Or are they just sort of unhealthy, and when they get vitamin C, there's no physiological drive for vitamin C, but when you get vitamin C, you just kind of feel better and you eat whatever makes you feel better. So, I mean, I can't answer that question. And I don't think there would be anything for vegetables. There has to be some
Some kind of
thing,
nutrient.
right? Some nutrient. And so where, there's this sort of field of thought called wisdom of the body, that the body is wiser than us. And if we just let ourselves choose, we would choose healthy kind of in a way. If you just took a child and didn't put all the social and stuff on them and just let him choose, then maybe the body would choose wisely. And there's several papers that suggest that's true, and there's several that suggest that's not true. The body's not always wise. So I don't know. I was actually worried that protein may not work as strongly, and I don't think it works as strongly as energy does. I think the regulation of energy is much more robust than that. The response to energy deprivation is really robust compared to, I think, the response to sodium, for instance, and oxygen especially, compared to protein. So I think it just gets weaker over time, and maybe just there is no regulation at a certain point.
To go along with that, like your body is always going to try to find the most energy it can as quickly as possible because that's the way we're wired. And so vegetables are really low in energy density, and so they're not going to provide as many calories as some of your higher energy density foods, which is why when we study human responses to food, people tend to prefer things that pack in the calories, and that's an evolutionary thing. So.
Yeah, there's a whole kind of thrifty gene kind of idea that we were really driven to gain weight and not really driven to lose weight, and so some people don't agree with that.
Do you think there is something related to the human being evolution about these signals that sent to the brain? Because before, my mom always said that right now the portions are huge and people just eat them. So there is something that it changed through the years, or it's just because we eat what we have in them?
Yeah, I mean, so I was expecting to get this question. Why don't these mechanisms defend against weight gain? Why are we obese? And I talked about leptin resistance. You give leptin to a low-fat fed, it works. You give it to a high-fat fed, it doesn't work. You do things that enhance leptin sensitivity, you don't get weight gain on a high-fat diet. But it's not really answering your question, but in my opinion, there's sort of three kind of arguments for why obesity occurs, right? Why have we gained weight recently? And the first is that the system's just broken. That obesity somehow breaks the system. Either it's broken previously because of genetics or some early life thing, or that the consumption of high-fat diet in obesity, that little initial obesity somehow breaks the system and it doesn't work. And there's support of that. Leptin resistance is a real thing. There's hypothalamic inflammation that occurs with diet-induced obesity, all that sort of thing occurs. So I think there's arguments to prove that. Another is that, we kind of touched on that before, that the energy balance system is weighted to defend against starvation, because that was theoretically prevalent in evolutionary biology, but not weighted to protect against obesity, because that was not very prevalent. So that's kind of this idea of thrifty genes. We're sort of designed to gain weight when we can in order to protect ourselves against weight loss. It's just that from thousands of years you didn't really gain weight when you could because there wasn't that much food. It's only now that we have excess food all the time, and that sort of manifests. And then the final is that the hedonic systems, so palatability, sweetness, and the food industry's ability to tap into what we love, it just overpowers this sort of system we have. So the system works. If you all just lived on water and rice cakes, it would work because there's no reward. But we live on Twinkies and Bluebell ice cream and Coke and all this other stuff that just is too powerful for leptin and AGRP and all to defend against. And I don't know if any of those are true. I think there's truth to a lot of those. I do know that the one thing I have with a third, so Hans Rudy, I hope, will talk about homeostatic versus hedonic feeding and kind of that interaction and the BTA and some other stuff. I don't know how much he's going to talk about that, but I think he will. The one problem I have with that is that there's many, many mouse models of obesity. You knock a gene out and they become obese. And none of those are in reward pathways. They're all in hypothalamic, so NPY, POMC, leptin, ghrelin. Now it's true that those hormones act on the reward system, but if you knock out dopamine and you knock out nucleus accumbens and all this sort of norepinephrine and all, it doesn't really cause obesity. So you can't just break that and cause obesity like you can break homeostasis and cause a homeostatic system. Those are too narrow of definitions, but still. So I don't know if I really answered your question, but I think it's all the above. I also have a feeling that physical activity, that our body is designed to regulate around a number of calories that's actually larger than 2,000. If we all burn 4,000 calories a day, even if we had unlimited access to food, our system's made to sort of equilibrate around 4,000 or 3,500. I saw a video once of these guys who were clearing the forest in Oregon back in the late 1800s, and they ate 5,000 calories a day because the trees would be as big as this room and they were hand sawing them down, right? And they weren't fat, but they ate 6,000 calories a day because they burned all this. And maybe the amount of energy, maybe it's just not robust enough to regulate the difference between 1,900 and 2,100 calories a day. It's just, if you get up to 3,000, it can regulate between 3,000 and 3,400. That's just me talking, right? But it's all this sort of interacting with, as well as Twinkies are readily available and cheap, and salmon and low steak and vegetables are relatively expensive, and all that stuff goes together, right?
I have a naive question with regard to your experiments. So we keep talking about increase and decrease in, especially like for example the protein deficit or the hormones. In these experiments, you have calibrated measures on how low of a protein, like the liver is already buffering and compensating immediately. So what concentration now of proteins, either in plasma or are you detecting to say this animal is protein deficit?
Yeah, that's
because you can really see it.
So how do we know our protein deprived animals are actually protein deprived?
Yeah.
So that's more difficult than you might think, right? So we know they're protein deprived because there's no protein. So our control is 20% casein and our low protein is 5% casein. So it's a 75% restriction. They're only getting 25% of what they might normally get. So they're definitely being protein restricted, and it stunts growth. They stop growing mostly, then they gain a little bit. So it's having physiological consequences. But if you measure blood amino acids, they're not much lower. I think if you measured portal vein amino acids, which you've never done, they would be a lot lower. And we've started measuring genes that are in the liver that are associated with amino acid biosynthesis. And for instance, ASNS, asparagine synthetase, it goes up like 300-fold with protein restriction because that gene helps you make asparaginase. You can make it, it's not essential, you can make it. And the gene associated with serine biosynthesis goes way up. And if you just fast an animal, they don't really change because they're not really being protein deprived in that state. So the best answer I can say is that physiologically and kind of mRNA expression, their liver looks like it's protein deprived. But whether their muscle is protein deprived, I don't know. And that's why I think FGF21 is important. It's this, the liver is making the rest of the body not be protein deprived, but it's talking to the brain and saying, hey, the gut and portal circulation in the liver detects insufficient dietary protein intake, and there's this emergency signal produced that is FGF21. That's what I hope is true, although I don't know.
So in the case of the hormone, did you ever compare the systemic level of the hormone versus the ICV injection concentration to see if that's...
So when you inject an ICV, it's not physiological in that way. I mean, it's very difficult. Okay. And I think the amount of FGF21 in the brain, we tried that one time because we did some we had some old microdialysis samples when we were measuring third ventricular amino acid concentrations. And we tried to measure FGF21, but it was too low for us to see. But So, and at that moment, actually, I wasn't sure if it was acting in the brain or not. It's only more recently with these brain-specific knockouts that we have a much more, evidence suggests that it's actually in the brain.
Maybe one quick question. So you described a lot about the protein-carbohydrate balance. Do you expect the same thing for protein-fat balance?
Yeah, that's a good question. I should say that there's actually some papers that show that high carbohydrate also drives up FGF21. So it's induced by low protein and independently induced by high carb, which from if you think about a hummingbird or a bear or whatever, it kind of doesn't matter, right? It's only our human situation that those things can be isolated the way they are. Fat I don't know about. We haven't done much with fat. We tried a little bit with fat, but it's a problem because as soon as you start messing with fat, body weight changes, energy density changes, all that stuff. So it's much more experimentally difficult. If you believe Steve Simpson, the guy who kind of coined the term protein leverage, he's done a lot of work where you feed diets that are different in their macronutrients. He argues that animals prioritize protein over the other two macronutrients. So they have a protein target that they try to seek, and that's the first. They have a carbohydrate target that they try to seek, but it's less important than the protein carbohydrate, and there is no fat target. So fat's just coming along for the ride, and that's why a high-fat diet causes you to overeat, in his mind, because it's diluting out the carbohydrate and the protein, and so you have to eat more to get those two targets, and so you overconsume energy. And he would argue that there is no energy balance target, that there's a carbohydrate and protein target that drive food intake. I don't know about that, but his data is kind of convincing. So I didn't quite answer your question because I don't know the answer.
Do we know what causes FGF21 to be produced? Like, is it coupled to a biosynthetic pathway, or is it just whenever amino acids are deficient? It's
okay. So I have to get my work in progress Tuesday. If you want to come listen, I'll show you what I did. But and one of my grant is transcription regulation of FGF21 with low protein. So we're working on that, and the answer is, the simple answer would be that yes, we do know some of the circuits or some of the molecules, and that one that is important but not as important as I wanted it to be is this kinase called GCN2. So what it means doesn't matter. But GCN2 is turned on by amino acid restriction. It's actually turned on all the way back to yeast by the accumulation of uncharged tRNAs. So when you think about biochemistry, you've got ribosomes and messenger RNA, and the tRNA goes and grabs the amino acid, and there's a different tRNA for each amino acid, and it brings it to the ribosome. And so when the tRNA binds to its amino acid, it's charged. And when there's not enough amino acids, you've got these unbound tRNAs or uncharged tRNAs, and when those accumulate, I don't know the methodology of it, but that turns GCN2 on. GCN2 phosphorylates eukaryotic initiation factor 2 alpha, and that does two things. It turns off protein translation in general, so the ribosome stops working. And that makes sense. You don't want to be trying to make proteins when there's no amino acids. But it also turns on this stress response pathway called the integrated stress response. And in particular activates this transcription factor called ATF4. And for instance, we talked about liver protein causes ASNS, asparaginase synthase, to go up. ATF4 binds to that and causes it to be expressed. If you take a yeast and amino acid deprive a yeast, ATF4 coordinates the expression of all the biosynthetic enzymes so the yeast can take ammonia and carbon and make its own amino acids, which yeast can do, but we can't quite do. So FGF21 has ATF4 binding sites, and ATF4 drives FGF21 to go up. And when we knock out GCN2, we knock out the ability of low protein to increase FGF21, and the GCN2 knockouts look like FGF21 knockouts. So that answer your question?
yeah, it's interesting.
Problem is that that only works transiently, and after like a week, the GCN2 knockouts FGF21 start to go up. So something's compensating for the absence of GCN2 long term. But we think that that's upstream of ATF4 because we're just doing studies in ATF4 knockouts, and I hope that it will never compensate. So something besides GCN2, there's other EF2 alpha kinases, and we think some of them may be being activated, so that's where we are.
So lots of interest here. I'm going to say, I want to thank you for the presentation.
No problem.
And if there are other questions, maybe you
Yeah,
can
I'm happy to talk,
interact
for sure.
on an individual basis here. So,
Sure.
yeah, thank you.